Good morning. All right, so yesterday we threw an audible out there because just a lot of people had not taken the test and stuff like that, and a lot of people have labs overdue. We need to get those things in so that I can grade them, put them in the grade book. If you don't do something, the grade becomes a zero. There's nothing I can do on that. The more zeros by the end of the semester you have, the lower your grade is going to be. Not going to be pretty if you have not done a lot of the work. Keep in mind, some of the work is completion and stuff like that. Like, for example, the Mythbusters, but laboratories are graded. You always have the opportunity to go through and look over those labs and then fix your mistakes that I've marked and then resubmit them and let me know that you need me to regrade it if that is the case, because sometimes the math and stuff like that is not totally correct. I got people taking the test that haven't done the lab, and then they don't do very well on the test because the math requirements for the test are in the laboratory. So keep that in mind. Make sure that you try to keep up. Otherwise, when you go to take a test, you're going to end up with not such a good grade on it. All right, let's take a look then. Hopefully you've printed out this quantum mechanics sheet, or you've downloaded it at least. Says state standards are here. Here are the standard-based objectives. We want to write something called the electron configuration. We want to be able to write something called the noble gas configuration. We want to be able to calculate the wavelength of something. We want to fill in this box diagram of something. So in order to do that, we need some rules. So if you would, go ahead, and if you want to number these pages, this would be page number 2. Might be a good idea. Last semester, you learned about the atom. Now, I'm sure that this is not your first study of the atom. You probably learned about it in previous years as well, maybe 5th grade and 7th grade. But the atom is made up of protons, neutrons, and electrons. The protons and neutrons, are in this thing called the nucleus. The electrons are around that nucleus. Our whole focus with this unit is dealing with electrons. Non-nuclear chemistry, or what we call inorganic chemistry, deals with electrons. Electrons is what causes the bonding, causes the reactivity. How matter behaves is based on electrons. So that's what we focus on here. Those electrons follow these rules. The Heisenberg uncertainty principle. If you've seen the movie Breaking Bad, Heisenberg was a German scientist. That's the name that Walter White picks, and it's based off of this scientist who was a German scientist during World War II. So Heisenberg uncertainty principle, it is impossible at the same time to determine both the location and direction of an electron. At best, we can only determine the possible or probable location. Why is that true? Well, it's because they're moving so fast. And if we want to find the direction that they're moving, we have to watch them along a path. If we watch them along a path, we cannot know where they were, because we're going to look basically where they're going to be. If we want to look at their location at any given point in time, we have to stop them. If we stop them, we can't see which direction they're moving. Electrons are very weird in this. In reality, an electron that moves out that door could end up in JEL. We wouldn't see it move through the hallway down the hall to JEL. It walks out that door. As soon as it walks out the door, poof, it's in JL. It doesn't move in that path that we expect it to take. And that's the weirdness of it. That's the quantum mechanics of it. If it gets enough energy, poof, it can go up an energy level. Just like if you were standing on one step and all of a sudden you were 2 steps higher. Nobody witnessed you walk from that step to the 2 steps higher, but it's like if you were at that step and then poof, all of a sudden you were 2 steps higher. That's the idea. There's no in between with this. That's what quantum means. The Schrodinger equation is basically a 3-dimensional mathematical equation that gives you x, y, and z of space. And these spaces are spaces around the nucleus. Orbitals are these XYZ coordinates, these locations, these solutions to the Schrodinger equation. Imagine if you were to open a tackle box or a jewelry box and you have these little separate places where you can put things. Those are like orbitals. Except the stuff we're putting there is not tackle or anything. It's jewelry, or it's not jewelry or, your sinkers. It's electrons. That's the only thing that goes in these orbitals. The rest of it is empty space. An orbital is a region where we expect to find electrons with a 90% probability. Pauli is an Italian scientist before World War II, very popular. Pauli came up with the Pauli exclusion principle. One orbital can, at maximum, hold only 2 electrons. That's it. Imagine this, you're going to sit at a McDonald's or something like that, and you're sitting in a booth. Usually those booths can only hold 2 people, right? Now, are each side of the booth equal? If so, then you probably wouldn't sit 2 people in one side of the booth and one, and 0 people on the other side of the booth. You would split them up, 1 and 1, that type of thing, right? But at max, each of those could only hold 2. Here's the thing: the Aufbau principle states that electrons must fill closest to the nucleus first. So let's imagine that one seat was better than the other. Then that seat may fill up before the next one. What does it mean, closest to the nucleus first or lower energy? Well, that means that if you look back at that old diagram, that S, that 1S, your whatever teacher told you it can hold 2 electrons, right? The first energy level, they put that ring around the nucleus, they put a 2 there, that at max it can hold 2 electrons. That is of lowest energy. All right? Why is that of lowest energy? You don't want to tell me. I know you got the talkative group, but why is closest to the nucleus of lower energy? Anybody a baseball player? Landon, you play baseball? Landon, have you ever hit a baseball with a baseball bat? No. Never? You've always struck out. Cassidy, have you ever hit a baseball or a softball or whatever with a baseball bat?
No.
No. You guys play any sports? Golf. We've got somebody in here that plays golf. Where do you hit the golf ball? What if we were looking at the stick? Where's the head? Close to your hands or far from your hands? Far from your hands, right? Close to your hands, whenever you swing a baseball bat or anything, there's not as much energy there. But further from your hands, at the edge of that stick, that's where the energy is. So when we talk about the alpha principle, electrons of lowest energy are closer to the nucleus. It's the same thing with nunchucks, right? If we take a look, where are the nunchucks the easiest at, right? Whenever you see somebody that's using nunchucks, they always take it and catch it closest to where it's spinning from. Because if you get hit from the end here, when it's swinging out there, way out there, that's how you actually have an impactful hit. So whenever you're catching it, you always catch it close. That's why they always keep it really tight inside of there, right? They always hit the person that they're trying to attack with the end out here because that's where all the power is, right? Keep that in mind. Same thing with a baseball bat. If you've ever watched a movie where somebody was trying to hit another person with a baseball bat, person hitting the other person with a baseball bat wants to hit them with the furthest part, just like the golf club. If somebody's trying to defend against a baseball bat, they try to grab it closest to the hands because that's where the lowest power is. That's where the lowest energy is. So when those teachers told you a long time ago, there's our nucleus, that first ring can only hold 2 electrons. That's what they were talking about. These 2 electrons will fill in first. Questions there? We call that the first principal energy level, or the first PEL. The first PEL has what we call 1 s orbital. And remember, orbitals are where electrons can exist. 1 s orbital, or s sublevel, has 1 orbital. And at most, it can hold 2 electrons. That's it. Oh, thank you. Huh. I don't see it anywhere around there. Weird. Because it's maximized, maybe. So here on this periodic table, the first electron every element has. Hydrogen has that electron as well. And it is in the first principal energy level, and it is very close to the nucleus. The second energy level is the second electron to go in is the second electron, which helium has, the first one of these, and then every element after helium, it also goes in the same place. So the first principal energy level is that first ring that your elementary teacher told you about. That represents the s sublevel, which has 1 orbital, and 1 orbital at most from the Pauli exclusion principle can hold 2 electrons. So here's what we have to memorize. Sublevels, not too difficult. SPDF, those are the ones that we worry about. The S sublevel can hold 2 electrons. That's because it only has 1 orbital. The P sublevel can hold 6 electrons. So basic math, how many orbitals must the P sublevel have? If the S sublevel holds 2 electrons with 1 orbital, How many orbitals must the p sublevel have to hold 6? 3. Good. Must have 3. The d sublevel holding 10 must have how many orbitals? Home players? Anybody? They're saying it in class. They're correct. 5. And the F sublevel has how many orbitals if it can hold at max 14? Worried about the home players. Well, if you can't do addition, subtraction, or multiplication and division, if 2 can be held in 1, and 6 can be held in 3, and 10 can be held in 5, you can't do the multiplication division. 7 is correct. You could also look at it as the prime numbers, 1 or the odd numbers, 1, 3, 5, and 7. Right? So these are the number of orbitals for each of these. So whenever your teacher told you, okay, around that first part is a ring, they may have sat there and drew it something like this and said, okay, here we have an electron, here we have an electron. The problem is that this next one, the second principal energy level, has the ability to hold how many? Anybody remember? The first ring can hold 2. The next ring can hold...
Isn't it 8?
It is 8. Very good. Can hold 8. So how can we get 8 from this? Well, we have to have an S and a P, because an S can hold 2 and a P can hold 6. So the second principal energy level not only has an S, but it also has a P. The third principal energy level has an S, P, and D. The fourth principal energy level has an S, P, D, and F. The fifth principal energy level would have an S, P, D, and F, and something else that we don't really care about, because it's too much for our periodic table. Maybe not even exists. But that's the basic idea. So the first energy level we would call 1s. The second energy level has a 2s and a 2p. The third energy level has a 3s, a 3p, and a 3d. Fourth energy level would have a 4s, a 4p, a 4d, and a 4f. And these all stack. We would continue with 5th, 6th, and 7th, but we don't care about a lot of the stuff. Like the 7th energy level has 7 sublevels. Well, we don't care what they are because we don't need all the sublevels. Remember, there's only a finite space around the nucleus, and bigger and bigger and bigger atoms don't exist really. Atoms are microscopic for a reason, because they only exist if they have a small number of electrons and around the nucleus. So how many electrons can fit in the following? First energy level is 2. That's that ring that 5th grade, 6th grade teacher told you about. That first ring. As was said in here, I believe by Sydney, that the second has S and P, which is 8. The third would have S, P, and D, which is how many electrons total? S, P, and D, 18, right? 18. And the next one would have 18 plus 14, which is 32. Can anybody figure out the math for this? 2, 8, 18, 32. There is a formula there. Anybody figure out that mathematical formula? How do we go from 2 to 8 to 18 to 32? Anybody figure out what the fifth energy level would hold? All right, let's try this then. We know that this is the SPDF. There is something else after F. If this is 1, 3, 5, 7, what's the next number in sequence after 1, 3, 5, 7? 9. So then we have 1 plus 3 plus 5 plus 7 plus 9. 1 plus 3 plus 5 plus 7 plus 9.
That would be 25.
There we have 25. 1 plus 3 plus 5 plus 7 plus 9, all right? So that would be 25. That's the number of orbitals. Each orbital can hold 2. So we multiply that by 2 and we get 50. 50 electrons, each orbital holding 2. So what we could do instead is 2, 8, 18, 32, 50. Well, if we have N, which is the principal energy level, the number of electrons equals 2N squared. If it's the first principal energy level, 1 squared is 1, times 2 is 2. If it's the second principal energy level, 2 squared is 4, times 2 is 8. 3 squared is 9, times 2 is 18. 4 squared is 16, times 2 is 32, so on and so forth. What is the mathematical pattern? I think that's just what I actually wrote. So I should write 2N squared here. What appears to be happening to electron capacity as their distance from the nucleus becomes greater? Well, imagine you're at a rock concert and or whatever concert you like, and the lead singer comes out into the crowd. How many can be right around him at once? Right? Maybe 3 to 4 people can be right up close, all together around him. And then as you get away, further and further, what do we see? There's more space there. So there can be more people, in a sense, closer to him. As we get far, far away, like the last row in a theater usually has the most seats, right? The same idea here. As we get further and further away from the nucleus, we have more space for electrons to exist. Right? If we look at it as like let's go to the mall. We want to go to the store. There are only so many parking spots like really close to the store. As you go a little bit further out, you have more parking slots that are the same distance to the store because you have a bigger diameter out there, right? So what I want you to do tonight is page 3, 4, page 4. So the number of sublevels that would exist in each of the following, the number of sublevels equals N. So if it has N equal 2, it has an S and a P. So it's 2. If N equals 36, it has an SPDF and then 32 other ones we don't care about. But it has 36 sublevels. List the number of orbitals that exist in each of the following. Well, sublevels, we know that S, P, D, and F have 1, 3, 5, and 7 orbitals respectively. We also know that the principal energy level, or N, equals 2N squared is the number of electrons, N square would be the number of orbitals. So if it's 3p or 5p, it doesn't matter. It's p, so it has 3 orbitals. Done. If it's the ninth principal energy level, 9 squared is 81. Number of electrons. Well, if we take that N square as the number of orbitals, we know every orbital equals 2 electrons. We know that P has 3 orbitals. 3 times 2 is 6. It doesn't matter if it's the 2p or the 5p, still holds 6. It just means that the 2 is closer to the nucleus than the 5p. If it's the entire energy level, n equals 3, well, we know that n squared equals the number of orbitals. So 3 squared is 9. 9 times 2 is 18. Again, 6f versus 205f. Well, every f holds 7 orbitals. Every orbital holds 2 electrons. So we have 14 and 14. Doesn't matter. The 6 and the 205 just tell us how far away from the nucleus they are. I'd like for you to complete page number 4 for this evening. Looks like I have some questions up here. Hopefully they remember I don't look at these very often. Okay, their answer's good. But that's what I got for today. If you have questions, by all means, stick around. Otherwise, have a great day.